Welcome back to section 6 of chapter P. In this section, we're going to be looking at complex numbers. Now, complex numbers have a couple different facets to them. Some of them are really easy, where you probably would never even need to be told what to do with it. Some of them are a little bit trickier. So even if you kind of remember, it's probably a good idea to pay attention to those, like multiplication, division, powers. Those are things that people tend to make mistakes on. There's also a little bit of new notation, just a tad. I threw it in there just in case you see it. So let's take a look. Our learning targets for today. We can add, subtract, and multiply complex numbers. We can write radicals in terms of I. We can find values of x and y to make equations true. We can write a complex number in standard form. And we can multiply a complex number by its conjugate. That's a problem coming up here in just a second. So, complex numbers. What are complex numbers? Complex numbers are the numbers that involve imaginary numbers. What are imaginary numbers? Imaginary numbers are those numbers that are not real. Great definition, right? We get imaginary numbers by doing things like finding the square root of -4. Well, what times itself equals -4? Well, 2 times 2 is going to be +4, and -2 times -2 is also +4. So how can we multiply something by itself and end up with a negative number? Well, that negative inside the square root just comes out and becomes an I on the outside. And the square root of 4 is 2. So we just reduce the root, and then the negative becomes an I. It's an imaginary number. One of the fun things about this, most of math was developed because it was needed for something. Like it was developed for a purpose. They had a problem to solve. Imaginary numbers and complex numbers were developed because someone said, hey, I wonder what happens if I do this. And they tried it, and the system was closed. It was complete. It was beautifully logical, and then it took quite a while before uses were actually found for it. Electrical engineering and stuff uses complex numbers, so there are definitely uses for it now, but it was developed just to see what would happen if. So that's kind of fun. Let's say it's not like a square root of -4. Let's say it's a square root of -20. Well, we're still going to have an I. And then the square root of 20, what does that reduce to? 20 is 4 times 5. 4 is going to be 2 and 2. So we have 2 root 5 I. That root was a train wreck. So that's how to write radicals as imaginary numbers. Not a horribly big deal. And now we get to the complex numbers. Now a complex number, this is a complex number in standard form, a plus bi. We have this a here. This is the real part. We have this b over here. Sometimes people go with the whole bi, but technically the b is the imaginary part. And then we have the I. The I is called the imaginary unit. If I was ever a masked wrestler, I would want to be called the imaginary unit. So that's what complex numbers look like. We want to write them so we have the real part plus the imaginary part. And so this 2 root 5i, that would be in standard form. The real part is just 0. We can use things in standard form to solve for x and y, like we saw in the learning targets. And this is remarkably easy here. Because if we have, say, x plus yi equals 4 minus 3i, we have real parts. We have x and we have 4. The real parts have to be equal to each other. X equals 4. And then we have the imaginary parts. Yi has to be the same as -3yi. y equals -3. That's all there is to that. There really isn't anything else. It could be, say, 2x plus yi. So we'd have 2x equals 4, so divide by 2, x equals 2. But those problems always look a little bit harder than they actually are. Operations with complex numbers. Some of these are super easy. For instance, addition. Basically, combine like terms. That's all it is. You can treat the I like a variable, with exceptions that we'll get to in just a second. But for addition, you combine like terms. Right here, the parentheses aren't doing anything. So we could look at the real parts, 3 plus 9. That's going to be 12. And the imaginary parts, 5i minus 2i is plus 3i. There it is, standard form and everything. Subtraction, basically the same. One slight little difference. Take this negative sign and make sure you distribute that. So we'll have a -6 plus 7i. Now we still combine our like terms. We have our real parts. 4 minus 6 is -2. The imaginary parts. -5i plus 7i is plus 2i. That's the addition and subtraction. Again, that's the part where even if you had never learned that, chances are if you had to make a guess, you would have probably guessed correctly. Multiplication. Basically the same, except we have to distribute because it's multiplication, just like if these were x's. We're going to take the 3 and multiply it to both those. And we're going to take the 2i and multiply it. So here we have 3 times 5 is 15. 3 times -i is -3i. 2i times 5 is plus 10i. 2i times -i is -2i squared. Now we're going to combine our like terms. However, in our standard form of our complex number, we did not have an I squared. That's because we can reduce I squared. I equals the square root of -1, which means I squared, if we square that, we get -1. But wait, you might think to yourself, now when you square a number, you get a positive. It's always positive. You're almost correct. When you square a real number, you get a positive. This isn't a real number, it's an imaginary number. So we can get that -1. So basically what this I squared does is it makes -1, which goes away, and it just changes that sign right there. So now we have 15 plus 2 is 17. -3i plus 10i is plus 7i. So that's the multiplication. That right there is the difference between an I and a variable when you're doing computations like this. It can be treated like a variable, except I squared equals -1, so it reduces. How about some powers of complex numbers? This is one where people tend to make a mistake. They tend to do something that I tell people never to do. Don't be that guy. And then I always get people that are like, nope, I'm going to be that guy. I'm going to do this. I really want to get some questions wrong on the homework, the quiz, the test, and I'm going to do it this way. So what I'm saying here, this 2 plus 3i squared, this is not, get a different color here, 2 squared plus 3i squared. It is not that. What it is, 2 plus 3i times 2 plus 3i, and then we have to multiply, just like we just did. 2 times 2 is 4. 2 times 3i is going to be plus 6i. 3i times 2 is another plus 6i. 3i times 3i plus 9i squared, but that I squared makes that a negative. So we have 4 minus 9 is -5, plus 6i and 6i is 12i. There we go. That's what it is. It is not 2 squared plus 3i squared. What if we had something cubed? I have 2 plus 3i cubed. Well, it's the same thing. This is going to be 2 plus 3i times 2 plus 3i times 2 plus 3i. Well, do 2 at a time. We already know from right up here that when we multiply 2 of them, we're going to get negative 5 plus 12i times 2 plus 3i. Now we distribute this. Negative 5 times 2 is negative 10. Negative 5 times 3i is negative 15i. 12i times 2 is plus 24i. And 12i times 3i is going to be plus 36i squared, but that I squared becomes negative 1. And so we have negative 10 minus 36 is negative 46. Negative 15i plus 24i is going to be plus 9i. And we could then take that times another 2 plus 3i to get 2 plus 3i to the fourth. And we could keep going from there. More operations, we have division. So division, we have 3 plus 2i divided by 1 minus 4i. All right, how would we divide a complex number? The short answer is you really don't. You multiply by the complex conjugate. What is the complex conjugate? The complex conjugate changes the sign on the imaginary part. We'll see in just a minute that a lot of complex numbers come from the quadratic formula, and in there we get a plus or minus the square root of something. Well, so we have those two solutions. One's plus the root, one's minus the root. Those are the conjugates. Definition here, the complex conjugate of z equals a plus bi. A lot of times we'll call complex numbers z, so we don't have a whole bunch of a plus bi. So we could have like z1 equals this, z2 equals this, then we can go z1 plus z2. But the complex conjugate is a minus bi. Now, I have this part in here because this is notation for complex conjugate. The z with a bar above it means the conjugate of z. And it just changes the sign. So here, the conjugate of 1 minus 4i is 1 plus 4i. And when we multiply, what that's going to do is that's going to get rid of the imaginary number. So we'll have just a real number in the denominator, at which point we'll be able to split up the fraction and we'll have it in standard form. But I can't just go around multiplying denominators by 1 plus 4i wherever I feel like it, all willy-nilly like. If I do that, I also have to do it to the numerator. So 1 plus 4i. So a division problem really just turns into two multiplication problems. We multiply the top. 3 times 1 is 3. 3 times 4i is plus 12i. 2i times 1 is plus 2i. 2i times 4 is plus 8i squared. But that's going to be a minus 8. And then the denominator, 1 times 1 is 1. 1 times 4i is plus 4i. Negative 4i times 1 is minus 4i. Oh, hey, look at that. These guys, plus 4i, minus 4i, those go away. That's the whole idea behind the conjugate. Same thing, the complex conjugate, the regular conjugate, it's the same idea. And then negative 4i times 4i is going to give us negative 16i squared, and that ended up in the wrong color, but that goes away there. Then just simplify. The numerator, 3 minus 8, is negative 5. Then 12i plus 2i is plus 14i. Over 1 plus 16 is 17. That is not standard form yet. Standard form is not a fraction. It's a plus bi. So we need to split this up. Negative 5/17 plus 14/17 I. Done. So that's all you have to do for division. It's just two multiplication problems. Lots of distribution. So we're going to try one, and by we, I mean you are going to try one, and then we'll come back and go over it really quick. So this one, we have 2 minus I times 1 plus 2I over 5 plus 2I. Has multiplication in the numerator, and then it has division. So this one has a couple extra steps. So right now, what you're going to do is you're going to pause this video. You're going to make sure you have a pencil and paper in front of you, and you're going to give this question a try. When you're done, unpause the video and we'll go over it. If you get hungry in the middle, make yourself a sandwich. It doesn't matter. You have as much time as you want to get this thing done. So go ahead and pause your video and come on back when you're ready. All right, how'd you do? First of all, did you do it? Did you pause your video? If not, pause your video now, go back, do the problem. It's part of the learning process. All right, now if you're ready to go on, let's look at these. So the first step, let's multiply out the numerator before we deal with the whole division thing. So we have 2 times 1 is 2. 2 times 2i is going to be plus 4i. Negative I times 1 is negative I. Negative I times 2i is negative 2i squared. But that's going to be a positive. The denominator is going to stay the same. I'm going to combine my like terms here. So we have 2 plus 2 is 4. 4i minus I is plus 3i. All right, over 5 plus 2i. All right, now we can multiply by our conjugate. The conjugate of 5 plus 2i, 5 minus 2i. Same thing to the top, 5 minus 2i. So now when we multiply, we get 4 times 5 is 20. 4 times negative 2i is minus 8i. 3i times 5 is plus 15i. 3i times negative 2i is negative 6i squared. We'll fix that in just a second. 5 times 5 is 25. 5 times negative 2i is minus 10i. Then we're going to have a plus 10i. 2i times negative 2i is going to be negative 4i squared. All right, the I squared makes that positive, I squared makes that positive. Combine our like terms. 20 plus 6 is going to be 26. Negative 8i plus 15i is plus 7i over 25 plus 4 is 29. And then the negative 10i plus 10i goes away. Split it up. 26 over 29 plus 7 over 29i. Now, is 7i over 29 technically the same? Yes, it is. With the form a plus bi, it is better to have the fraction than the I following it. Technically, it doesn't make that much of a difference, but it is slightly more proper to write it like this than it would be to have the I in the numerator. So, using complex roots of solutions of quadratic equations, where do these things even come from? A lot of times they come from the quadratic formula. They can also come from just solving quadratics. So if we had, say, x squared plus 9 equals 0, and we were solving this using square roots, we'd subtract 9. X squared equals negative 9. Root both sides. X equals plus or minus 3i. So the I comes there. Anytime we get a square root of a negative, the I comes. So a lot of times it'll come from the quadratic formula. So as we're looking at a quadratic, x squared plus x plus 2 equals 0, we can put it into the quadratic formula. X equals negative b, that's 1, plus or minus the square root of b squared, 1, minus 4 times a times c, all over 2a. I don't know what that line just came from. So x equals negative 1 plus or minus the square root. This is 1 minus 8, so that'll be negative 7 over 2. Well, the square root of negative 7 is going to involve an I in it, so that's negative 1 plus or minus root 7i over 2. We could put it into standard form, negative 1/2 plus or minus root 7 over 2i. And there it is. That's all that it is to it for the quadratic formula. We just end up with that square root, or that negative in the square root, pull it out as an I. Easy. Um, so the stuff inside the square root, that b minus 4ac, that's called the discriminant. If the discriminant is positive, you'll have two real solutions. That's where it crosses the x-axis like we saw earlier. If the discriminant is 0, you'll have one real solution. That's where it comes down, touches the axis, then goes up again. And if the discriminant is negative, then there will be no real solutions, but there will be two imaginary solutions, or two complex solutions. And that's what we have here. So